Nuclear fusion is a different story. We don't know how to make nuclear fusion work, as I said, except in thermonuclear weapons. We're working on the problem. We've been working on the problem since the 1950s. We keep saying it's a few decades off. It keeps being a few decades off. We're now making some real progress. I don't have time here to go into the details of the fusion technology, but let me simply say that if we got nuclear fusion to work, then every gallon of seawater, the special isotope deuterium of hydrogen in every gallon of seawater, would be enough to make a gallon of seawater the energy equivalent of 300 gallons of gasoline. So nuclear fusion, if we ever get it going, has considerable promise. It may end up being too expensive. It does produce some nuclear waste, not nearly as much as our nuclear fission plants produce and not nearly as long-lived. So it's a real possibility, but I think for a very distant future. And if we have a climate change problem, we've got to solve that problem long before that distant fusion future. What about solar energy? Well, I've argued that the solar flow is more than 10,000 times the energy humanity now uses. We have simple passive solar technologies like houses that have a lot of south-facing glass and not much north-facing glass and lots of insulation that can get a significant fraction of their residential heating and lighting energy from the sun. More complex active solar technologies do things like circulate water through simple thermal solar collectors and supply domestic hot water. In cloudy Vermont, where I live, I get 95% of my hot water from May to October from a solar domestic hot water system built into the roof of my garage. Another thing you can do with solar energy is concentrate it with a mirror-like device, boil water or some other fluid, and drive a conventional turbine or some other kind of engine and generate electricity that way. Perhaps the most exciting and promising solar application is photovoltaic devices. These are semiconductor devices that use silicon technology to convert sunlight energy directly into electricity with efficiencies that are typically around 15%, but could get as high as about 40%. They can be done as rooftop applications on individual homes or buildings, or in grid-connected power plants, up to some tens of megawatts or so, not a huge amount of power, but significant. It's spread out in either sunny regions or not such sunny regions, and nevertheless, they will convert sunlight directly into electricity. Solar photovoltaics and most forms of solar energy are not at this point economically competitive with other energy sources. That's partly because of our tax structure and some of the incentives we give still to fossil fuels, but it's also because we simply haven't developed those technologies enough. Nevertheless, solar photovoltaic installations are currently growing worldwide at about 40% a year. There are also indirect solar applications. Hydropower is indirect solar energy that we use to evaporate water. Wind, as I mentioned, about 1% of the incoming sunlight goes into driving the winds. When we harness wind energy with wind turbines, we're tapping into that flow. And finally, biomass, the growing of crops or trees or burning of wood or whatever living materials capture sunlight. They're not very efficient at it. They're only 1% or so efficient, but they grow all over the planet. And if we harvest that, we end up being able to burn it. For instance, we have wood-fired electric power plants that have huge piles of wood chips around them, and the power plant burns those wood chips and operates like a fossil-fueled plant. In fact, some plants can switch back and forth between the two. We're working on biofuels to generate gasoline-like substances that we can burn in our cars. Ethanol, particularly, is used in the United States to supplement gasoline. The way we produce it in the United States is not particularly efficient. It takes almost as much energy, sometimes more, to produce it. But Brazil, with its tropical climate, grows a lot of sugarcane, converts it to ethanol, and uses that to power much of its vehicle fleet. So biomass offers considerable promise, and biomass, although it's being burned and producing carbon dioxide, if it's harvested sustainably and without a lot of fossil fuel involved in processing it, it can become almost carbon neutral, meaning the trees you replant after you cut them down, or the corn you replant after you cut the corn down, or the sugarcane or whatever, then takes as much carbon dioxide out of the atmosphere as was put in by burning the previous crop. So combustion of biomass does not need to be a net carbon source. I haven't mentioned one of the favorites of alternative energy people, and that is hydrogen. What about hydrogen? Hydrogen is an ideal fuel in many ways. It burns very cleanly. It produces only water vapor, which is a greenhouse gas, but not to the extent carbon dioxide is from burning fossil fuels. It doesn't produce other pollutants, but here's the rub. There is no hydrogen energy on Earth. Hydrogen has to be in the form of molecular hydrogen, H2, and all the hydrogen on Earth is already, quote, burned. It's mostly tied up in water and other compounds that are basically burned. So there is no hydrogen fuel. Hydrogen is not an energy source for us in the sense that other fuels are. It's an energy carrier. It's something we could make with other energy sources. We can use other energy sources to split water into hydrogen and oxygen. Then we can recombine them by burning or by using fuel cells, devices that combine them and convert the energy directly to electricity. There are many things we could do if we had hydrogen, but we don't have any hydrogen and we have to make it. And so the climate impact and the environmental impact of hydrogen is the same as the environmental impact of however we make the hydrogen. If we choose to run a coal-fired power plant and use the electricity from that power plant to make hydrogen, then we haven't done any better, and because of inefficiencies, we've probably done a little worse than if we had used the coal-produced energy directly. If we choose to make hydrogen with a nuclear fission reactor, then tied up in that hydrogen are all the environmental problems that are associated with nuclear fission reactors, for example. If we could perfect fusion and use fusion reactors to generate electricity or use their heat directly to split hydrogen, either way splitting hydrogen from water, then we might have an interesting source of hydrogen that would be fairly benign. Or, better yet, if we could find a way to take sunlight and directly break up water, which there are ways to do. It's called photolysis, not a very efficient or economical process. Then we could make hydrogen directly from sunlight energy. Or we could build photovoltaic power systems, use the electricity to split water into hydrogen and oxygen, and we'd have hydrogen. Hydrogen would be a great energy carrier in some future economy. It's going to be a long time coming. It's not going to come soon enough to solve our greenhouse warming problems. And we have to remember there isn't any hydrogen fuel available to us. We have to make it, and we have to make it in a benign way. Well, finally, let me end by reminding you something else about all these energy sources. Although many of them are better in terms of pollution and climate impact than the fossil fuels, no energy source is perfectly benign. No energy source is perfectly benign. And I want to show you at the end of this lecture a graph that looks at greenhouse emissions from different energy alternatives and scales them relative to each other. For the fossil fuels, we're pretty sure we have a good handle on that. And so I'm showing you for the fossil fuels low and high values of actual technologies in terms of the amount of carbon dioxide emitted in grams per kilowatt hour of energy coming out of these fossil fuels. The worst is coal, the next is oil, the next is natural gas. Those are the fossil fuels. We expect that the fossil fuels are bad in terms of producing carbon dioxide, if I can call that a bad thing. And I think I can, because we're worried about global climate change caused by that carbon dioxide. But next comes solar photovoltaics. They're much harder to estimate, but the energy used in making the silicon, the high purity silicon that's used in making semiconductors, consumes a lot of fossil fuel. So the high estimate for photovoltaic energy is that it is a significant fraction of the carbon dioxide produced from natural gas, because of the fossil fuels used in its manufacture. Most of us would argue that it's actually a lot lower, and the low estimate is very small, and as we develop new photovoltaic technologies, that number will go down. Hydroelectricity in the temperate zone can be very, very free of greenhouse emissions, but in the tropics, it can produce large amounts of greenhouse emission, as I mentioned, from the methane that's being burned. Biomass can be done either sustainably or not so sustainably, processed with a lot of fossil fuels or not, and may or may not be greenhouse neutral, and nuclear may produce some greenhouse emission, largely from the processing of nuclear fuels and the building of concrete to make reactors. No energy source is benign, but all the energy sources other than fossil fuels are a lot better, at least from a climate standpoint.